And valence bond theory actually tells us that central metal atom makes available a number of atomic orbitals, empty atomic orbitals. Okay. And how many empty atomic orbital do we need? We need that many atomic orbitals which are equal to the number of ligands or the coordination number. And these empty atomic orbitals undergo hybridization. That's what we have seen. So they undergo intermixing. So the purpose of hybridization is to make them homogeneous so that they can form the bonds well. So depending upon the number of bonds, or which is the coordination number, you need to take that many empty atomic orbitals that we have seen in the last class. We have also seen some examples. Okay. Let's try to figure out some more examples and the drawbacks and how to get rid of those drawbacks. Okay. We have seen this is I hope it's clear to all of you. Any doubts in the previous class? Jaslina, Aisha, Marwa. Any doubts?
No, sir.
Okay. So basically, when we were trying to discuss the arrangement of nickel, then we had a problem. Okay. What problem we had, right? In the geometry and hybridization. What problem we were facing? Can you tell me? That nickel with the 4 chloride ions, that is tetrachloride or nickel 2, was square planar. The word tetrahedral. Okay. While on the other hand, tetracyanide or nickel 2 was square planar. There was also a difference in magnetic moment. Okay. So with that, we started with the drawbacks of valence bond theory. Is it clear? The drawbacks. So valence bond theory is unable to predict the geometry of coordination number 4. Geometry and hybridization of complexes with coordination number 4. Clear? Because in some cases, we found that the geometry is tetrahedral. Okay. For NiCl4, it is like this. But for NiCl4, it is perfectly square planar. So why it may be happening, Jasleen? Can you tell me?
Sorry, sir.
Yeah, why this is happening? That one of the nickel is actually uh, tetrahedral, forming a tetrahedral complex with four ligands, while another one is forming a square planar complex. Are you getting my point?
Is it due to different electronic configurations?
Yeah, different electronic configuration, but nickel plus two is same. So why the electronic configuration has changed? And why the geometry has changed? So change in geometry due to difference in electronic configuration, that's true. But what led to the change in the geometry and the shape for NiCl4? It is tetrahedral. Got it?
Lone pairs.
Yeah, lone pair could be one of the options.
uh, is because CN is a more strong ligand compared to
Yes, exactly. So the main thing is that the ligands are strong and weak. And until and unless you know that, you will not be able to successfully predict the electronic configuration of the ions. Got it? Is it clear?
Yes, so
So this is the drawback of valence bond theory. We were discussing the drawbacks that valence bond theory is unable to predict the geometry of the complexes connected to four ligands. Valence bond theory is unable to predict whether the complex is going to be square planar or is it going to be tetrahedral. Is it clear? So this is lacking in valence bond theory. We have seen example just now, as you can see here, that we have seen the example of nickel connected to four ligands with four chlorido ligands and four cyanido ligands. With chlorido, it was a tetrahedral complex. With cyanido, it was a square planar complex. But why is it is happening? Pure valence bond theory is unable to predict what may be causing this. Is it clear or not? Okay. And the main reason is the valence bond theory doesn't differentiate between the strong and the weak ligands. Is it clear? Doesn't differentiate between the strong and the weak ligands. So because once you are able to differentiate between the strong and weak ligand, you can clearly solve this problem. Valence bond theory is also unable to predict the magnetic behavior of the complexes, the color of the complexes. Is it clear? For example, nickel 2 plus ion in water forms this complex. While in ammonia, it is going to form this complex. The color is green and blue. So why the same nickel is forming a green colored compound with water, but it is formed, and why it is forming the blue colored compound with ammonia? What's the reason? VBT doesn't have any answer. Actual answer is we will be discussing. We will know once you have the differentiation between the VBT between the weak and the strong ligands. And this weak and the strong ligand differentiation is adopted from the other theory. Is it clear? And that theory is actually the CFT, crystal field theory. Okay. So before starting that crystal field theory, let me take some point of the crystal field theory in valence bond theory. And valence bond theory, if you try to differentiate between the ligands as strong and weak ligands, you can easily uh, classify them as strong and weak, and you can easily predict the geometry and the color of the complexes. And the magnetic behavior of the complexes also you will be able to predict. So let me write the ligands, the strength of the ligand, and that is spectrochemical series. So what do you mean by spectrochemical series? It is a series which tells us about the increasing order of the strength of the ligands. Got it? So can you tell me what is the strength of the ligands? If you remember, Jasin, Aisha, Marwa. Any idea about the strength of the ligands and the spectrochemical series?
So the highest is CN.
Yeah. So first of all, the halogens are weak ligands. Got it? Is it clear? Halogens are weak ligand. So you have I minus, Br minus, SCN minus. SCN is thiocyanate to S. It is an example of an ambidentate ligand. Got it? Is it clear? Then
Yes, sir.
you have Cl minus sulfide ion, NO3, F, OH, After the wet, you have acetate, acetate is going to be CH3COO minus. Then after acetate, you have oxalate. Oxalate is C2O42 minus. Got it? Then you have H2O. So water is weak liquid. Is it clear or not? Water is a weak liquid. And after water, you will start with nitrogen containing ligands, which are strong ligands. Generally, they are considered to be strong. NCS, EDTA. Got it? NS3, PY. PY is the pyridine. So all these nitrogen containing ligands are considered to be the strong ligand. Got it? PY is pyridine. What's the formula of the pyridine? Can you tell me? What is going to be the formula of pyridine? C5. It is just like a benzene ring with one nitrogen ring. Got it? Then you have En, NO2, Cn, and CO. So this beyond water, you have strong ligands. All the nitrogen containing ligands are strong ligands. Okay, is it clear or not?
Yes, sir.
So this point has been Maro adopted from, it has been adopted from crystal field theory, but if we apply it in valence bond theory, so most of the drawbacks of the valence bond theory which we were having, they will be rectified. Jaslin, is it clear?
Yes, sir.
Okay. So what they try to do, so now we have more clarity regarding the strength of the ligand. And these ligands actually are classified into strong and weak. The nitrogen containing ligands are strong ligands. Okay. And what they will do, then how they will change the shape, how they will change the magnetic behavior of the complex. You can make out very clearly by knowing that the strong key ligands will try to make the unpaired electrons paired. Are you getting my point or not? So what strong field ligands will do? They will make the unpaired electrons pair up. Unpaired electrons of whom? Unpaired electrons of the metal ion. They will get paired up. Is it clear or not? Are you getting my point?
Yes, sir.
Okay. So just remember the spectrochemical series. This is actually a a series which tells us about the strength of the ligands. If you have the clarity on this, you can draw the shape and the structure of any complex, and you can successfully predict its electronic configuration, its shape, its geometry, and hybridization. So let's do some examples by considering the spectrochemical series. Got it? For example, let's say we try to draw FeF6 3 minus. Okay. So first thing is, which is the central atom? Tell me.
Fe.
Yeah. Try to find the oxidation state. Right? What is the oxidation state of Fe? And what is first try to find out the electronic configuration of the Fe. Fe is the 26th element. Right? So 26, I told you how to remember the electronic configuration. 26 means 2 and 6. Got it? 2 and 6 means 4s2 and 3d6. Is it clear?
Yes, sir.
Nickel is 28. So 2 and 8. 2 in the S and 8 in the inner D. Is it clear or not? So this is what is the oxidation state? What is the charge on iron?
+3.
+3. Okay. If you don't know the charge, it is very easy to find out. Let it be X. Okay. X, and the charge of the fluorine is -1. So there are 6 fluoride ions. So -6 equal to -3. X equal to +3. So the charge is +3. +3 means I have to remove the 3 electrons. Got it? From the outermost shell. So how I will do? I will remove the 2 s electrons, and 1 electron from D I am going to remove. So Fe+3 I have written here. You can see, right? And from Fe to Fe+3 I have removed 3 electrons. 2 from the 4s and 1 from 3d. So 3d is left with only 5 electrons. You can see here. Can you see it? Now F minus. What kind of ligand is F minus? And how many are they? Is it a strong or a weak ligand?
Weak ligand.
It is a weak ligand. You can see this boundary. Okay, nitrogen containing ligand, Aisha, Marwa, Jasleen, they are strong. Water and before water are weak. F minus is very weak. Okay. So weak ligand will not do the pairing. Is it clear? They will not pair up the unpaired electrons. Got it?
Yes, sir.
So Marwa, how many F minus are there? 6. I need 6 empty orbitals. To connect F minus, I need 6 empty orbitals where F minus can donate its electron pair. So tell me which 6 empty orbitals I am going to choose.
5 3D and 4s1.
Yeah, this 4s. So we are going to start from this 4s, 4p. So 4 we have already chosen, and 2 orbitals, empty orbitals from 4d need to be chosen. They are going to, before bonding with F minus, we will make them same, homogeneous, and that process is known as hybridization. Got it? The hybridization is going to be sp3d2 hybridization. Is it clear or not? Why sp3d2, Jaslin? Am I audible? Why do I need to need to make it sp3d2? Why sp3? Because there is one 4s orbital, okay, 3 from 4p, and 2 from 4d orbitals getting involved in hybridization. So that's why the name sp3d2 hybridization. Okay. And how many hybrid orbitals will be there? 6 of them, because one S that got hybridized and changed itself to sp3d2. What will be the name? Their name. They will be named after the name of the hybridization. So there will be 6 sp3d2 hybrid orbitals. Got it? And where they will be pointing? They will be pointing towards the corner of a regular tetrahedron. So Fe will have empty orbitals, 6 of them. Before hybridization, they were different. One was S, the 3 were the 4p. Okay, they became same, because I want to make them participate in the bond formation. So I need to make them same by mixing them. That process is known as hybridization. Okay, 6 sp3d2 hybrid orbitals, and because they are 6, how they are going to put themselves around the iron plus 3 iron? They are going to put themselves around in such a way so that the minimum repulsion is there between them, and they will acquire an octahedral arrangement. Octahedral arrangement is like this, in which 4 of the bonds are in the plane. Is it clear? 4 of the bonds are in the plane. One of the bond is at the top, another bond is at the bottom. Got it? So six groups will be there, and the 2 adjacent bond angles, how much it will be? Jaslin, can you tell me the bond angle? Aisha, Marwa, in octahedral complex, the bond angle between the 2 nearest groups and the 2 farthest groups. What is going to be the bond angle?
90 degree.
Pardon? The 2 nearest is?
90
Yes,
degree.
exactly 90 degrees. This is 90 degrees. And the any 2 which are farthest or opposite, one at the top, another at the bottom. That is how much? 180. Okay. So this is ligand, ligand, ligand. L represent ligand. Okay. And so we have this iron, and in our example, the one which we were doing, the ligands were F minus. So now this these 6 hybrid atomic orbitals will accept the lone pair from F minus. Is it clear or not?
Yes, sir.
And you will have an octahedral complex. In this, you can show these F minus electrons by different symbols like this. These are the pair of electron. I am putting these yellow crosses, okay, to show you the pair of electrons which were donated by F minus into the empty orbitals of iron 3 plus, leading to the formation of Fe F6 3 minus. Got it? The hybridization is sp3d2. What is the magnetic moment? Is it going to be a paramagnetic or a diamagnetic species? Is it going to be a paramagnetic or a diamagnetic? Are there unpaired electrons on the iron? And how many are they? How many unpaired electrons are there? Am I audible to all of you? Yeah, Jasleen, Marwa, Aisha. So how many unpaired electrons are there? On the iron? Yeah, Aisha, tell me. Marwa, tell me.
The 5 unpaired
Yeah,
electrons.
5 unpaired electrons. So what is the magnetic moment?
Paramagnetic.
Yeah, it is paramagnetic, and the formula for the magnetic moment, which is a measure of how strongly the complex or the compound is going to feel the attractive force in the magnetic field, that is under root n into n plus 2. And the unit is Bohr magneton, where n represent the number of unpaired electrons. Got it? In this case, n equal to 5. So the magnetic moment is going to be under root 35. We know, all of us know, under root 36 is 6. And under root 35 will be somewhere around 5.9. So pure valence bond theory was unable to predict the electronic configuration and the geometry hybridization. There were some problems, right? But when we adopted some of the part of the crystal field theory, which we are going to study after this, all our problem got sorted out. What we adopted from crystal field theory, we adopted the strength of the ligand, order of the strength of the ligand, which classified the ligands into strong and weak ligands. Is it clear?
Yes,
Strong ligands will force the unpaired electrons to pair up, and the weak ligands will let them remain unpaired of the metal ion. F minus was a weak ligand, and the electrons unpaired which were there on the iron triplet, they remained unpaired. And F minus used the outer orbitals for the formation of bonds. Right, this is outer orbital complex because the d orbital are the outer 4d orbitals. Is this clear, Jasleen? Is it clear, Aisha, Marwa?
Yes, sir.
Next thing is, what is going to happen if you try to form a complex whose formula is FeCN6? There are 6 cyanide ligands, 3 minus. If you notice that this is the same iron 3 plus, the charge of the iron is 3 plus, but instead of F minus, we are dealing with 6 cyanide ligands. Got it? So now, will there be any difference? The electronic configuration of Fe3 plus, I'm going to write iron was 26th element, 2 and 6 as I told you. Plus 3 means I need to remove the 3 electrons, 2 electrons from the 4s and 1 electron from the D. And these are the 3D electrons. 5 of them are going to remain. 4s is going to be empty because it had 2 electrons, they were removed because we made iron plus 3. Four P and 4D. Got it? Now we have 6 Cn minus ligands. What kind of ligands are Cn minus? Have a look at
Strong.
this strong ligands. NO2, Cn, Cn. They are strong ligands. And what they will try to do? Strong ligands will try to push the unpaired electrons inside and they will pair them up. If there is a possibility of pairing, if there are unpaired electrons. Got it? So Cn minus ion will push the unpaired electrons and pair them up, right? But all of them cannot get paired because they are odd. Jaslyn, am I audible?
Yes, sir.
Yeah. So I hope you are getting why I have paired up. It is because of the strong ligands. And who got paired up? The ligand, the electrons of the central metal atom or ion. Who is responsible for pairing them up? The strong ligands. If there is a possibility. For example, if all are already paired, you can't pair them up, right?
But
Yeah, clear?
sir, isn't
Hmm.
there a rule saying that we have to fill all the orbitals first, then start pairing?
That was for isolated atoms in the class level. That was there, okay? That was, yes, that was for the electronic configuration of iron when you are writing. So first you put one electron each and then you start pairing. Exactly, you are right. But this is not the isolated iron. This is the iron which is surrounded by 6 strong field ligands. Marwa, are you getting the point?
Yes, sir.
So what you are absolutely correct, but when you are absolutely correct, if you are dealing with isolated atom, but is the central atom isolated now? No, it is surrounded by the ligands. So what and strong ligands? What strong ligands will try to do? They will force the unpaired electron to pair up. Is it clear?
Yes, sir.
So in the presence of a strong ligand, the pairing can occur even if they are not singly filled. Okay. So if they are unpaired, you will push them inside and make paired them. But all of them will not get paired because we were having 5 electrons. So you were having 2 pair of electrons and one remain unpaired. Who is responsible for this? This strong ligand. Got it?
Yes, sir.
Now I need to this electrons got paired up and I need 6 empty orbitals so that I can attach my 6 ligands. So which 6 empty orbitals do I need to take? Empty orbitals of iron I need so that I can attach the CN minus ligands with the help of the lone pair. Actually, the CN minus ligands are going to donate their pair of electrons to the empty orbital of the iron. Is it clear or not?
Yes.
Okay. So, how many empty orbitals I'm going to use to bond Cn minus ions?
4s, 4p.
4s, yeah, 4p. And these two are also empty. Why not use them also? Why unnecessarily go up to 4D? We did that in the previous complex. We had gone up to 4D and we have started, Jaslin, Aisha, from 4s. Why we have started using empty orbitals from 4s? Because they were occupied, they were not free. But because of this pairing has emptied some of the d orbitals and we can use them for the bonding with cyanide. Is it clear? Can you gauge the difference between the two? Marwa, Aisha, Wrestling. Any doubts in this? In that complex, I use outer D orbital from 4D. In this complex, I use 3D. Why? How come I use the 3D? In spite of having 5 electrons in 3D. But those 5 electrons got paired up. Who paired them up? The strong ligands. Is it clear?
Yes.
So this is, they are going to undergo intermixing and that this hybridization is known by the name of D2sp3. It is not sp3d2. There is a difference between them. Is it clear? Not this one, this one. D2sp3. Why D2sp3? Because I use the 3D orbitals inner, right? So that's why I'm going to use the D2sp3. Is it clear? And
Sir.
Yeah,
What's the difference between sp3 d2 and d2 sp3?
actually, suppose if you use the 3D orbitals, then 4s and 4p. If they are available, empty orbitals are available, then this hybridization is going to be d2sp3. And if the d orbitals are occupied, like in the above case, this one, no d orbital is empty. So I'm going to use 4s, 4p, and 2 of the 4d orbitals. So that's why the hybridization sp3d2. Is it clear?
Yes, sir.
And this can happen if the d orbitals are available, inner d orbitals, and this is inner orbital complex, if they are available. So I'm going to use them. And these crosses represent the pair of electrons donated by the cyanide ligand, Cn minus. Got it? The shape is going to remain same. It is going to be an octahedral complex. Cn, there are 6 cyanoligands around the iron. What is the magnetic moment of this complex? How can you make out whether the pairing has occurred or not? By knowing the magnetic moment. If the pairing has occurred, you will have less number of unpaired electrons, single electrons. So you can see the effect of pairing. In this example, there is only one unpaired electron. In the above example, we had 5 unpaired electrons. And that happened because of the strong ligands, which force the unpaired electrons to pair. Got it?
Yes.
So magnetic moment is going to be one electron, so 1 in under root 1 into 1 plus 2, so root 3. It is going to be 1.732. The units is Bohr magneton. This is paramagnetic. Because the single electron act like a magnet, unpaired electron, so it will get attracted towards the magnetic field. Got it? It will be paramagnetic in nature. But the force of attraction felt by it will be less because there is just one unpaired electron. In the case, in the above example, you were having 5 unpaired electrons. Got it? Here, so either
Yes.
the hybridization, if you have 6 groups, 6 ligands, listen to me very carefully, all of you. If you have 6 groups, either the hybridization is going to be D2sp3 That is going to happen if you use inner d orbitals for bonding. If they are empty, if they are available, or if they are made available by the strong ligands, which force the unpaired electron to pair. But if these inner d orbitals are not available, then you are going to use the outer one 4d orbital, 4s, 4p, and 4d for bonding. Got it? That complex will be outer orbital complex. So either both inner or both outer. Okay. Let's try to figure out the shape, geometry, hybridization, magnetic behavior of the complex NiH2O or NiNH3. NH3 is a strong ligand, 0.6 with +2 charge. First of all, you need to remember the atomic number from scandium to zinc. Scandium, titanium, vanadium, chromium, manganese. Manganese is a 26th element. Midpoint of the series. Midpoint is manganese. Iron, cobalt, nickel, copper, zinc. From 26 to 30. Nickel is the 28th element. If I talk about the nickel, it is nickel is 28th element, so argon. Don't write that complete electronic configuration. Okay, that is not used here. Just write the short form. You need to show that outermost valence electrons. Argon 3d 22 element. 3d8 and 2 in the outer core. Got it? But in our case, in our complex, this is not the nickel. This is Ni2 plus. Is it clear? Ni2 plus, right? So I need to remove 2 electrons. And how many electrons? The 2 electrons, that 4s electrons are going to remove. Outer electrons are removed, right? So you have argon 3d 8. 3d8, I'm going to write it in boxes, directly in the boxes, which we are going to use now. Is it clear? 3d 8 electrons. Four s 2 were there because you made nickel +2, you need to remove 2 electrons. 4p was already empty. So let it remain empty as of now. And 4d also was there. Okay, that was also empty. This is the electronic configuration of the nickel +2 cation. Now we need to attach the ligands. What kind of ligands are they? Strong or weak?
From
Strong ligands or weak ligands?
from
NH3. Let's go back to the spectrochemical sequence. NH3 is strong or weak?
oh sorry weak.
All the nitrogen containing ligand is the starting of nitrogen So which nitrogen is connected. Okay, this is not nitrogen. This is actually NO3 oxygen. It is connected to oxygen. So nitrogen, in which the nitrogen carrying a lone pair, they become strong ligands. Got it? So NH3 is a strong ligand. PY, pyridine, ethylene diamine, NO2, all of them are strong. Got it?
Yes, sir.
So we have 6 NH3 as strong ligands. Now be very careful. Okay, what will happen? What strong ligand usually do?
Pair up.
They will pair up the unpaired electrons. So let's pair them up. But is this pairing of any use to us? Is it of any use? Or it's just useless? One of the D orbital was made available by the pairing. Marwa, Jesslyn, Aisha, can you see it?
Yes, sir.
How many ligands are there? 6. But is it going to be any useful for the bonding? There's one empty D orbital from the 3D. Can we use it? And if we are going to use it, should we use it first of all? Tell me. How many empty D orbitals do we need? We need 6 of them to connect 6 NS3. But as I told you, either both, there are two D. Either it should be D2 sp3. Either both should belong to 3D or both should belong to 4D. Then only the bonding will happen. There is no point of doing any pairing in this case. Is everybody agreeing with it? Jaslin, can you hear me? Marwa, can you hear me? Aisha,
Yes, sir.
tell me quickly. Very, very important point. So, is there any point of doing the pairing? No. Because in coordination number 6, we need either 6 ligands which are inner or 6 or outer D orbitals. There were 8 electrons. We were getting just one D orbital, empty from the inner. That is of no use to us. Let it remain, let the electron remain unpaired. Even if you pair them, you are going to get only one of the D orbital, not two. In coordination number 6, either we need both inner or both outer. So let them remain untouched and let's use this outer D orbital. Is it clear to everyone? The
Yes, sir.
hybridization is going to be sp3d2 even with the strong ligand. So every time don't go by strong and weak. Okay, you need to look at other factors also, whether the strong ligand is causing the two empty d orbitals getting empty. Will they be available? Okay, that we need to check. Next question. This is the question from which we started our discussion in today's class. And we started discussing that this valence bond theory was unable to predict the geometry of the complexes having four groups. Sometimes they are tetrahedral, sometimes they are square planar. And valence bond theory was unable to predict the geometry. It was also unable to predict their magnetic moment. So we brought in that spectrochemical series. That spectrochemical series let us classify the ligands into strong and weak ligands. And from that, we came to know that strong ligands will not affect the electron, weak ligands will not affect the electronic arrangement of the metal ion, while strong ligands will tend to pair them up. Got it? So, all that we included in VPT to make it more accurate. So now let's compare both the complexes, their geometry, their hybridization, and their magnetic moment. Okay. Now we are also aware of the strength of the ligand. The halogens were weak ligands, Cl minus, Br minus. They were at the starting. While NO2, C and CO are the strong ligands, NH3 and beyond, all these nitrogen containing ligands are strong. So we can Cl minus is weak and Cn minus is strong. In both the cases, what is the oxidation state or the charge of the nickel? Who is going to tell me? Charge of the nickel.
Two plus.
Yes, plus 2. What will be the electronic configuration of plus 2? Nickel is the 28th element. So 28 means 8 and 2, 8 in 3D and 2 in 4s. And because it is plus 2, you need to remove the 2 electrons from the 4s. Got it? So nickel plus 2 is argon 3D8. Originally it was 3D8 and 4s2. But because it became plus 2, so we removed those 2 electrons from 4s. So now it is 3D8. Got it? So this is 3D8. Now, what are we going to do with these 8 electrons? What their fate will be? Fate with respect to pairing. Who is going to decide their fate? Whether these 8 electrons are going to remain as it is or are they going to get paired up? I need how many empty orbitals in this case?
4.
How many? Yeah, I need 4. The coordination number is 4. Correct. So, will the Cl minus force the unpaired electron to pair up?
No, it's a weak ligand.
Yeah, weak ligand. So it will not force the unpaired electron to pair up. We are going to leave them as it is, untouched. Let them remain in their original state only. And now, but I need 4 empty orbitals so that I can uh, connect the 4 chloride ions to the nickel. And those 4 empty orbitals are from 4s and 4p. I'm going to intermix them together, hybridize them together. The hybridization will be known as sp3 hybridization. It's not D2sp3, not sp3d2. I'm not connecting 6 again. I just need 4. And nickel, sp3 is tetrahedral. And once you have this tetrahedral, 4 empty tetrahedral pointing nickels. Of 4 chloride ions will donate their lone pairs and get connected to the nickel ion in a tetrahedral one. Cl minus, Cl minus, Cl minus, and Cl minus. Is it clear? It is going to be
Yes.
tetrahedral. And what is the magnetic moment?
2.
2 unpaired electrons. The magnetic moment, it is paramagnetic. It will be attracted by magnetic field. The magnetic moment is under root n into n plus 2, where n is the number of unpaired electrons. 2 into 4 root 8. So it is going to be 2.83. Bohr magneton is the unit. Got it? So you are either going to be asked about how the questions are going to be. They're going to ask the geometry, shape, unpaired electrons, magnetic moment, nature of the complex, whether it is paramagnetic or diamagnetic. If there are no unpaired electrons, all the electrons are paired up, then it is diamagnetic. If the unpaired electrons are available, then it is paramagnetic. It will be attracted by the magnetic field. Because as I told you, each unpaired electron acts like a magnet. NiCN4 2 minus. Ni plus 2 is there. Same nickel plus 2 is there. Same number of electrons. But we have 4 cyanidoligands. NO2, Cn, and Co were the 3 last strongest ligands. in the spectrochemistry. They were in the beginning, okay? They are the strongest of all the ligands. So they will force the unpaired electron to pair them up, right? And in the 3D, you can see the 3D above, okay, in nickel. I'm going to pair these two electrons, and total I will have 4 pairs with one entity orbital atom. Is it clear? Will it be useful that for me to form the bond? In octahedral geometry, that was of no use because octahedral geometry I need 2 inner or 2 outer. But either it was D2 sp3 or it should be sp3 D2. But this is not the octahedral geometry, not 6 ligands, just 4 ligands. With 4 ligands, this can be used. What's going to be the hybridization? DSP2. What's going to be the shape if it is DSP2? This is dx square dash y square, which is pointing along the x-axis and y-axis. So this complex, the ligands will also point along the x-axis and y-axis. It will be a square planar complex with 4 ligands at 90 degrees. Is it clear? These are the lone pairs. Why I have represented the electron in a different manner? Because these are the electrons from the cyanide atom. Got it? And this is DSP2. So it is going to be a square planar complex. What about the magnetic moment? Yes, am I audible? So all angles are 90 degrees. Is it clear? So in coordination number 4, if you have strong ligands and if pairing occurs, you will have a square planar complex with 90-degree bond angles. But with coordination number 4, if you have weak ligands, then it is going to be a tetrahedral complex. So Aisha, Marwa, and Jasmine, what can you say about the magnetic moment of this complex?
Dimagnetic.
Yes, it is a diamagnetic. And there were no unpaired electrons. N is 0. So the magnetic moment is going to be 0. N is 0, magnetic moment is 0. Okay. And diamagnetic complex will not be attracted in the magnetic field. Complex or the compound will feel attractive force only if it is having unpaired electron. Is it clear or not? So now I think you have a clarity. But that clarity came in by knowing the nature of the ligands. Sorry, and by knowing
the ligands and how they will affect the electronic configuration of the metal. By including the nature of the ligands, we were able to successfully predict the pairing will happen or not. That let us decide the empty orbitals were available for the bonding. That let us decide the empty orbital or the filled orbital available for the bonding, and that also helped us to predict the geometry and the magnetic behavior correctly. Is it clear? So that spectrochemical series is very, very important. Let me take another example. So in coordination number 4, if you have strong ligands, if pairing is possible, DsP2 square planar complex will form. But if you have a weak field ligands, okay, ligands which are weak, no pairing, let them remain as it is. Use the outer orbit, which are sp3, tetrahedral complex will be there. Okay, so now let me talk about the so just tell me what is going to be the hybridization of this complex. You are going to follow the step. First, write chromium. It is the 24th element. 24 is 2 and 4. Am I correct? But there is, am I correct or have I made a mistake here? What will be the, if it is incorrect, what is going to be the correct electronic configuration of the chromium? Marwa, Aisha,
3D2.
no, 3D5 actually, because half-filled electronic configuration is very stable. So in 11th class, you might have studied, and we are going to study again in DNF doc element that one electron moves from 4s to 3D, so that the 3D becomes half filled or fully filled. That happens in the case of properties. Okay, so this is going to be argon Pd5, because there's 5 electrons, just 1 electron in each is very stable, and 4s now. Now, this is for the chromium. Now, identify the charge of the chromium in the complex. What charge chromium will have in the complex? Oxidation number of the chromium. It is +3. Let it be x. X minus 6 equal to -3. So x should be equal to +3. Got it? Is it clear to everyone? Chromium +3 means I need to remove 3 electrons. So 1 from 4s and 2 from 3d. So chromium +3 is going to have this electron. It will have just 3 electrons left in the 3d. Because I removed 3 electrons, 1 from 4s and 2 from we have strong field ligands. Now we will, and we need 6 empty orbitals. Aisha, am I audible? Jasmine, am I audible
Yes,
to
sir.
everyone? Yeah. So now be careful, there is a change, slight change in this example. So tell me which hybridization. Are we going to pair up the electron? Cn is a strong ligand.
So will they remain unpaired?
Yes, why they will remain unpaired? They will remain unpaired. Even with the strong ligands, there is no need to pair up them. Why?
Hund's rule?
No. Actually, you already have 2 empty d orbitals available. Okay. You don't have to pair them further because you need 6 of them. Got it? You need 6 empty orbitals. Either they should be d2 sp3 or they should be sp3 d2. Either 2d inner from 3d or both outer 4d orbitals for hybridization. And without pairing only, you have already have 2 empty d orbitals available for you. Is it clear or not? Getting my point?
Yes, sir.
Yes.
So there is no need to pair them up now. You already have these two empty free radicals. Even if we pair them up, there is no hybridization called as D3sp2. No, either you D2sp3 or sp3. That you should keep in mind. So you already have two empty d orbitals. Okay. And it is going to be D2sp3 hybridized. Right? Even with the strong field ligands, you have not paired them up, you already were if available, that empty d orbitals were already available. So no need for pairing it up. Got it?
Yes, sir.
So let's so what do all your problems